Chapter 3 Atoms and Molecules. Ancient Indian and Greek philosophers have always wondered about the unknown and unseen form of matter. The idea of the divisibility of matter was considered long back in India. Around 500 BC, an Indian philosopher, Maharishi Kanad, postulated that if we go on dividing matter, this padartha, we shall get smaller and smaller particles. Ultimately, a time will come when we shall come across the smallest particle beyond which further division will not be possible. He named these particles Paramanu. Another Indian philosopher, Pakuda Katiyamma, elaborated this doctrine and said that these particles normally exist in a combined form which gives us various forms of matter. Around this same era, ancient Greek philosophers Democritus and Leucippus suggested that if we go on dividing matter, a stage will come when particles obtained cannot be divided further. Democritus called these three individual particles atoms, meaning indivisible. All this was based on philosophical considerations and not much experimental work to validate these ideas could be done till the 18th century. By the end of the 18th century, scientists recognized the difference between elements and compounds and naturally became interested in finding out how and why elements combine and what happens when they combine. Antoine L. Lavoisier laid the foundation of chemical sciences by establishing two important laws of chemical combination. The following two laws of chemical combination were established after much experimentation by Lavoisier and Joseph L. Proust. 3.1.1 Law of conservation of mass. Is there a change in mass when a chemical reaction takes place? Activity 3.1 Take one of the following sets X and Y of the chemicals. X copper sulfate 1.5 gram, Y sodium carbonate 1.43 gram. Second, barium chloride sodium sulfate 1.22 gram, 1.53 gram. Lead nitrate 2.07, sodium chloride 1.17 gram. Prepared separately, a 5% solution of any one pair of substance listed under X and Y, each in 10 ml in water. Take a little amount of solution of Y in a conical flask and some solution of X in an ignition tube. Hang the ignition tube in the flask carefully. See that the solutions do not get mixed. Put a cork on the flask. See the figure 3.1. Weigh the flask with its contents carefully. Now tilt and swill the flask so that the solutions X and Y get mixed. Weigh again. What happens in the reaction flask? Do you think that a chemical reaction has taken place? Why should we put a cork on the mouth of the flask? Does the mass of the flask and its contents change? Law of conservation of mass states that mass can neither be created nor destroyed in a chemical reaction. Law of constant proportion. Lavoisier, along with other scientists, noted that many compounds were composed of two or more elements and each such compound had the same elements in the same proportions, irrespective of where the compound came from or who prepared it. In a compound such as water, the ratio of the mass of hydrogen to the mass of oxygen is always 1:8. Always 1:8, whatever the source of water. Thus, if 9 gram of water is decomposed, 1 gram of hydrogen and 8 gram of oxygen are always obtained. Similarly, in ammonia, nitrogen and hydrogen are always present in the ratio 14:3 by mass, whatever the method or the source from which it is obtained. This led to the law of constant proportions, which is also known as the law of definite proportion. This law was stated by Proust as in a chemical substance the elements are always present in definite proportion by mass. The next problem faced by scientists was to give appropriate explanations of these laws. British chemist John Dalton provided the basic theory about the nature of matter. Dalton picked up the idea of divisibility of matter, which was till then just a philosophy. He took the name atoms as a given by the Greeks and said that the smallest particle of matter are atoms. His theory was based on the laws of chemical combination. Dalton's atomic theory provided an explanation for the law of conservation of mass and the law of definite proportion. According to Dalton's atomic theory, all matter Whether an element, a compound, or a mixture is composed of small particles called atoms. These postulates of this theory may be stated as follows. All matter is made up of very tiny particles called atoms, which participate in chemical reactions. Atoms are indivisible particles which cannot be created or destroyed in a chemical reaction. Atoms of a given element are identical in mass and chemical properties. Atoms of different elements have different masses and chemical properties. Atoms combine in the ratio of small whole numbers to form compounds. The relative number and kinds of atoms are constant in a given compound. You will study in the next chapter that all atoms are made up of still smaller particles. What is an atom? Have you ever observed a mason building walls? From these walls, a room and then a collection of rooms to form a building. What is the building block of the huge building? What about the building block of an ant hill? It is a small grain of sand. Similarly, the building blocks of all matter are atoms. How big are atoms? Atoms are very small. They are smaller than anything that we can imagine or compare with. More than millions of atoms, when stacked, would make a layer barely as thick as sheet of paper. We might think that if atoms are so insignificant in size, why should we care about them? This is because our entire world is made up of atoms. We may not be able to see them, but they are there and constantly affecting whatever we do. Through modern techniques, we can now produce magnified images of surfaces of elements showing atoms. What are the modern day symbols of atoms of different elements? Dalton was first scientist to use the symbols for elements in a very specific sense. When he used a symbol for an element, he also meant a definite quantity of the element, that is, one atom of that element. Berzelius suggested that the symbol of elements be made from one or two letters of the name of the element. In the beginning, the names of elements were derived from the name of the place where they were found for the first time. For example, the name of the copper was taken from Cyprus. Some names were taken from the specific colors. For example, gold was taken from the English word meaning yellow. Nowadays, IUPAC, International Union of Pure and Applied Chemistry, is an international scientific organization which approves the names of elements, symbols and units. Many of the symbols are the first one or two letters of the element's name in English. The first letter of a symbol is always written as a capital letter, uppercase, and second letter as a small letter, that is lowercase. For example, hydrogen, capital H, aluminium, capital A and small l, and not as capital A and capital L. Third, cobalt as capital C and small o, and not as capital C and capital O. Symbols of these some elements are formed from the first letter of the name and a letter appearing later in this name. Examples are first chlorine, that is Cl, second zinc, that is Zn, etc. Other symbols have been taken from the names of the elements in Latin, German or Greek. For example, the symbol of iron is Fe from its Latin name ferrum. Sodium is Na from natrium. Potassium is K from kalium. Therefore, each element has a name and unique chemical symbol. Table 3.1 Symbols for some elements. Element symbol. Element aluminium Al, argon Ar, barium Ba, boron B, bromine Br, calcium Ca, carbon C, chlorine Cl, cobalt Co, copper Cu, fluorine F, gold Au, hydrogen H, iodine I, iron Fe, lead Pb, magnesium Mg, neon Ne, nitrogen N, oxygen O, potassium K, silicon Si, silver Ag, sodium Na, sulfur S, uranium U, zinc Zn. The above tables given for you to refer to whenever you study about elements. Do not bother to memorize all in one go. With the assigned carbon and atomic mass of 1 point with the passage of time. So do not bother to memorize all in one go with the passage of time and repeat usage, you will automatically be able to reproduce symbols. 3.2.2 Atomic mass. The most remarkable concept that Dalton's atomic theory proposed was that of the atomic mass. According to him, each element had a characteristic atomic mass. The theory could explain the law of constant proportion so well that scientists were prompted to measure the atomic mass of an atom, since determining the mass of an individual atom was a relatively difficult task. Relative atomic masses were determined using the laws of chemical combinations and compounds formed. Let us take the example of compound carbon monoxide, CO, formed by carbon and oxygen. It was observed experimentally that 3 grams of carbon combines with 4 grams of oxygen to form CO. In other words, carbon combines with 4 by 3 times its mass of oxygen. Suppose we define the atomic mass unit earlier abbreviated as AMU, but according to the latest IUPAC recommendations, it is now written as U, unified mass, as equal to the mass of one carbon atom. Then we would assign carbon an atomic mass of 1.0 U and oxygen an atomic mass of 1.33 U. However, it is more convenient to have these numbers as whole numbers or as near to a whole numbers as possible. While searching for various atomic mass units, scientists initially took 1 by 16 of the mass of an atom of naturally occurring oxygen as the unit. This was considered relevant due to the 2 reasons. Oxygen reacted with a large number of elements and formed compounds. This atomic mass unit gave masses of most of the elements as whole numbers. However, in 1961, for a universal accepted atomic mass unit, carbon-12 isotope was chosen as the standard reference for measuring atomic masses. One atomic mass unit is a mass unit equal to exactly 1/12 the mass of one atom of carbon-12. The relative atomic masses of all elements have been found with respect to an atom of carbon-12. Imagine a fruit seller selling fruits without any standard weight with him. He takes a watermelon and says this has a mass equal to 12 units. 12 watermelon units are 12 fruits of mass units. He makes 12 equal parts of the watermelon and finds the mass of each fruit he is selling. Related to the mass of one piece of the watermelon, now he sells his fruits by relative fruit mass unit, as in figure 3.4. Similarly, the relative atomic mass of the atom of an element is defined as the average mass of the atom as compared to 1/12 the mass of carbon-12 atom. How do atoms exist? Atoms of most elements are not able to exist independently. Atoms form molecules and ions. These molecules or ions aggregate in a large number to form a matter that we can see, feel or touch. What is a molecule? A molecule is a group of 2 or more atoms that are chemically bonded together, that is tightly held together by attractive forces. A molecule can be defined as the smallest particle of an element or compound that is capable of an independent existence and shows all the properties of that substance. Atoms of the same element or different elements can join together to form molecules. Molecules of elements. The molecules of element are constituted by the same type of atoms. Molecules of many elements such as argon, helium, etc. are made up of only one atom of that element, but this is not the case with most of the non-metals. For example, a molecule of the oxygen consists of 2 atoms of oxygen and hence it is known as diatomic molecule, O2. If 3 atoms of oxygen united into a molecule instead of the usual 2, we get ozone. The number of atoms constituting a molecule is known as its atomicity. Metals and some other elements such as carbon do not have a simple structure but consist of a very large and indefinite number of atoms bonded together. Let us look at the atomicity of the non-metals. Table 3.3 Atomicity of some elements. Type of element non-metal. Name argon, that is monatomic, helium monatomic, oxygen diatomic, hydrogen diatomic, nitrogen diatomic, chlorine diatomic, phosphorus tetraatomic, sulfur polyatomic. Molecules of compounds. Atoms of different elements join together in definite proportions to form molecules of compounds. Few examples are given in the table 3.4. So compound combining elements ratio by mass. Water, hydrogen, oxygen 1:8. Ammonia, nitrogen, hydrogen 14:3. Carbon dioxide, carbon, oxygen 3:8. Activity 3.2. Refer to table 3.4 for ratio by mass of atoms present in molecules and table 3.2 for atomic masses of elements. Find the ratio by the number of atoms of the elements in the molecules of compounds given in table 3.4. The ratio by the number of atoms for water molecules can be found as follows. Element ratio by mass, atomic mass, mass ratio by atomic mass, simplest ratio. Hydrogen 1, atomic mass 1, mass ratio or by atomic mass, that is 1, simplest ratio 2. For element oxygen, ratio by mass 8, atomic mass 16, mass ratio by atomic mass is 1/2, simplest ratio is 1. Thus the ratio by number of atoms for water is hydrogen is to oxygen is 2:1. What is an ion? Compounds composed of metals and non-metals contain charged species. The charged species are known as ions. Ions may consist of a single charged atom or a group of atoms that have a net charge on them. An ion can be negatively or positively charged. A negatively charged ion is called an anion and a positively charged ion is cation. Take for example sodium chloride. Its constituent particles are positively charged sodium ions and negatively charged particles are called chloride ions. A group of atoms carrying a charge is known as polyatomic ion. Table 3.6. We shall learn more about formation of ions in chapter 4. Table 3.5 is some ionic compounds. Ionic compound constituting elements ratio by mass. Calcium oxide, calcium and oxygen 5:2. Magnesium sulfide, magnesium and sulfur 3:4. Sodium chloride, sodium and chlorine 23:35.5. 3.4. Writing chemical formulae. The chemical formula of a compound is a symbolic representation of its composition. The chemical formulae of different compounds can be written easily. For this, learn the symbols and combining capacity of the elements. The combining power or capacity of an element is known as valency. Valency can be used to find out how the atoms of an element will combine with the atoms of another element to form a chemical compound. The valency of the atom of an element can be thought of as hands or arms of that atom. Human beings have 2 arms and an octopus has 8. If one octopus has to catch hold of a few people in such a manner that all the 8 arms of the octopus and both arms of all the humans are locked, how many humans do you think the octopus can hold? Present the octopus with oxygen and humans with hydrogen. Can you write the formula for this combination? Do you get OH4 as the formula? The subscript 4 indicates the number of humans held by the octopus. The valencies of some common ions are given in table 3.6. We will learn more about valencies in the next chapter. Table 3.6 names and symbols of some ions. Valency 1. Name of the ion sodium, symbol Na+, non-metallic element hydrogen, symbol H+, polyatomic ions ammonium, symbol NH4+, potassium K+, silver Ag+, copper Cu+, magnesium Mg+2, calcium Ca+2, zinc Zn+2, iron Fe+2, copper Cu+2, aluminium Al+3, iron Fe+3, hydrogen H+, hydride H-, chloride Cl-, bromide Br-, iodide I-, oxide O2-, sulfide S2-, nitride N3-, ammonium NH4+, hydroxide OH-, nitrate NO3-, hydrogen carbonate HCO3 minus, carbonate CO3 2 minus, sulfite SO3 2 minus, sulfate SO4 2 minus, phosphate PO4 3 minus. The rules that you have to follow while writing a chemical formula are as follows. The valencies or charges on the ion must balance. When a compound consists of a metal and non-metal, the name or symbol of the metal is written first. For example, calcium oxide CaO, sodium chloride NaCl, iron sulfide FeS, copper oxide CuO, etc. Oxygen, chlorine, sulfur and are non-metals and are written on the right, whereas calcium, sodium, iron and copper are metals and are written on the left. In compounds formed with polyatomic ions, the number of ions present in the compound is indicated by enclosing the formula of ion in a bracket and writing the number of ions outside the bracket. For example, MgOH2 bracket close. In case of the number of polyatomic ion is 1, the bracket is not required. For example, NaOH. Formula of simple compounds. The simplest compounds, which are made up of two different elements, are called binary compounds. Valencies of some ions are given in table 3.6. You can use these to write formulae for compounds. While writing the chemical formulae for compounds, we write the constituent elements and their valencies as shown below. Then we must cross over the valencies of the combining atoms. Examples: formula of hydrogen chloride. Second, formula of hydrogen sulfide. Formula of carbon tetrachloride. For magnesium chloride, we will write the symbol of cation Mg+2, first followed by the symbol of anion, that is chlorine minus, then their charges are crisscrossed to get the formula. Fourth, formula of magnesium chloride. Formula MgCl2. Thus, in magnesium chloride, there are two chloride ions, that is Cl minus, for each magnesium ion Mg+2. The positive and negative charges must balance each other and the overall structure must be neutral. Note that in the formula, the charges on the ions are not indicated. Some of the more examples: formula for aluminium chloride, aluminium oxide Al2O3, formula for calcium oxide CaO2, formula of sodium nitrate NaNO3, formula of calcium hydroxide CaOH twice. Note that the formula of calcium hydroxide is CaOH twice and not as CaOH2. We use brackets when we have two or more of the same ions in the formula. Here the bracket around OH with a subscript 2 indicates that there are two hydroxyl groups joined to one calcium atom. In other words, there are two atoms each of oxygen and hydrogen in calcium hydroxide. Formula of sodium carbonate Na2CO3. In the above examples, brackets are not needed if there is only one ion present. Formula of ammonium sulfate NH4 twice SO4. Molecular mass and mole concept. Molecular mass. In section 3.2.2, we discussed the concept of atomic mass. This concept can be extended to calculate molecular masses. The molecular masses of substance is sum of the atomic masses of all the atoms in a molecule of their substance. It is therefore the relative mass of a molecule expressed in atomic mass unit. U. Formula unit mass. The formula unit mass of a substance is the sum of the atomic masses of all atoms in a formula unit of a compound. Formula unit mass is calculated in the same manner as we calculate the molecular mass. The only difference is that we use the word formula unit for those substances whose constituent particles are ions. For example, sodium chloride, as discussed above, has a formula unit NaCl. Its formula unit mass can be calculated as 1 into 23 plus 1 into 35.5 is equal to 58.5 unit. Mole concept. Take an example of the reaction of hydrogen and oxygen to form water, 2H2 plus O2 forming 2H2O. The above reaction indicates that two molecules of hydrogen combine with one molecule of oxygen to form two molecules of water, or 4 units of hydrogen molecules combine with 32 units of oxygen molecule to form 36 unit of water molecules. We can infer from the above equations that the quantity of substance can be characterized by its mass or the number of molecules, but a chemical reaction equation indicates directly the number of atoms or molecules taking part in the reaction. Therefore, it is more convenient to refer to the quantity of a substance in terms of the number of its molecules or atoms rather than their masses. So, a new unit, mole, was introduced. 1 mole of any species atoms, molecules, ions or particles is that quantity in number having equal to its atomic or molecular mass in grams. The number of particles, atoms, molecules or ions present in 1 mole of any substance is fixed with the value of 6.022 into 10 to the power 23. This is an experimentally obtained value. This number is called as Avogadro constant or Avogadro number, represented by N naught, named in honor of Italian scientist Amedeo Avogadro. 1 mole of anything is equal to 6.022 into 10 to the power 23 in number, as 1 dozen is equal to 12 numbers, so 1 gross is equal to 144 numbers. Besides being related to a number, a mole has one more advantage over a dozen or a gross. This advantage is that mass of 1 mole of a particular substance is also fixed. The mass of 1 mole of a substance is equal to its relative atomic or molecular mass in grams. The atomic mass of an element gives us mass of one atom of that element in the atomic mass unit is U. To get mass of 1 mole of atom of that element, that is molar mass, we have to take some numerical value but change the units from U to G. Molar mass of atom is also known as gram atomic mass. For example, atomic mass of hydrogen is equal to 1 unit, so gram atomic mass of hydrogen is 1 gram. 1 unit hydrogen has only 1 atom of hydrogen. 1 gram of hydrogen has 1 mole atoms, that is 6.022 into 10 to the power 23 atoms of hydrogen. Similarly, 16 unit oxygen has only 1 atom of oxygen. 16 gram oxygen has 1 mole of atoms, that is 6.022 into 10 to the power 23 atoms of oxygen. To find the gram molecular mass of molar mass of a molecule, we keep the numerical value of the same as the molecular mass but simply change units as above from unit to gram. For example, as we have already calculated molecular mass of water, H2O is 18 unit. From here we understand that 18 unit of water has only 1 molecule of water. 18 gram of water has 1 mole of molecules of water, that is 6.222 into 10 to the power 23 molecules of water. Chemists need the number of atoms and molecules while carrying out reactions, and for this they need to relate the mass in grams to the numbers. It is done as follows. 1 mole is equal to 6.022 into 10 to the power 23 number is equal to relative mass in grams. Thus, a mole is the chemist counting unit. The word mole was introduced around 1896 by Wilhelm Ostwald, who derived the term from the Latin word moles, meaning a heap or pile. A substance may be considered as a heap of atoms or molecules. The unit mole was accepted in 1967 to provide a simple way of reporting a large number, the massive heap of atoms and molecules in sample. Thank you.